Good day, everyone. So this is day 2 of our Python programming class. And this training, we're only going to learn machine learning with Python. So how we can use Python to do machine learning regression. We are going to consider multiple linear regression, random forest, Gaussian process regression, and artificial neural network. So these are the 4 models we are going to learn in this training currently going on. The first training I use it to explain the basics of Python so that you can familiarize yourself with Python language. For this training, we are using the Jupyter Notebook ID. Let me share my screen. So the first step, we are going to go to our Jupyter Notebook and go to an account and launch Jupyter Notebook. So this is our Jupyter Notebook. You can open a new file and start writing codes. I have my file I want to use, so I'll locate the file. The file is on my desktop. So I prepared it before I started this video. What I'm going to teach today is multiple linear regression. Then in the next class, I will teach either artificial neural network or random forest. Gaussian process regression will be the last model we are going to learn. So I'll explain how to do multiple linear regression with Python. The first thing you have to know is you have to import the packages you need, the libraries you need. You have to import them. So you need to know the libraries, the packages you need, and import them. So that's the first thing. So the dataset I'm going to use for this class is on Boston housing dataset. So let me explain what this dataset is all about. Data we are collected from Boston, and it's on housing price. Like you want to estimate, you want to predict, or you want to value a particular building. So the dependent variable, my battery, let me charge. Sorry for that. Let me charge my laptop. Okay, so the data is on Boston housing pricing. So you want to value, to know the worth of a particular building, the worth of a particular building, the price of a particular building. So you can do that by using neighborhood characteristic, like the crime rate in that particular city. You can also check the air pollution, check how close the building is to maybe university, employment centers, and different things. So these are characteristics that we are going to use to predict housing prices. So let me give you more details about the dataset. So this is the dataset. This is a brief introduction about the dataset. The dataset we are going to use is from Boston housing, and the dataset is from, you can get it at Kaggle or scikit-learn package. Look at the variables we are going to use. This is the predictor, the response variable, sorry. Then these are the predictors. So we are predicting the median value of owner-occupied homes. And what we are going to use to predict it is the average number of rooms. So if you tell me the average number of rooms in your residential building, you tell me the proportion of homeowners in the neighborhood considered as low status, like people around your building, are they considered low status, to be of lower status? If you tell me the pollution, like nitric oxide concentration in that city, you tell me the crime rates, you tell me the proportion of non-retail business acres per town. So these are information you have to tell me. When you give me all this information, I can use it to predict the value of your residential building, the worth of your residential building. We know if you want to sell your building or you want to know how much your building costs, you can call a surveyor to give you an estimate. So we are trying to use a model to do that. First, we'll start with multiple linear regression. Then we'll consider other models and see how they perform in predicting or estimating the worth of a building. So these are the predictors we are going to use in the regression model. So we have 13 predictors and one response variable. So let's go back to this. So I'm going to fetch the data from Python. Now, this data set I just explained, I just talked about, is in scikit-learn. So we are going to use scikit-learn. Scikit-learn. The data set is in scikit-learn, and we are going to import this from scikit-learn. So we have to install if you don't have all these, so if you don't have the scikit-learn library, you have to install it. So how do you install it? You do pip install, so you use scikit-learn to install it, then run. I already have it in my system, so it will tell me I already have it. Then after installing it, you have to restart the kernel. How do you do that? You go to kernel and click restart and clear, or any of these. So you have to restart. You can use restart or restart and clear. So let me restart. So after installing, you do that. You also need, we're going to use this to make plots. So you can install matplotlib. Matplotlib. So you install. After install, you can install everything before restarting. That's okay. If you don't have this, then you have to also install it. NUMPY. We can use that to work on our data set and do some calculation. So you install it. I already have it. Then after installing all you need, you restart your kernel. So let me restart again. First, you install, then next you have to import. So you import the library or module you need. So after installing it, you start importing them. So I installed this. So instead of me writing this name every time, I can decide to use a simple name for it. NP, that's the popular name people use. You can use any other name. It's not like it is fixed. So instead of me writing this NUMPY every time, I can just write NP. We'll be making use of this. We'll also make use of the matplotlib. So in this library, we are going to get this module. And we are going to call it PLT. So whenever I call PLT, it means all this. Instead of me writing all this every time, we use this matplotlib to make plots. We use it to make plots. So later, we are going to make plot and compare all the models, how all the models perform. We are going to use the matplotlib. Then to fetch our data set, we are going to use the scikit-learn. So sklearn. When you want to install it, you have to spell it as SCIKIT, then dash. This is what I mean. If you want to install, you spell it like this. You do pip install scikit-learn. But after that, we will be calling, when you want to import it, we use sklearn. So let that not confuse you. But it's the same package I installed, the same library I installed. So now from this library, we have different data sets. So from scikit-learn data set, I want to import this function, fetch openML. I'm going to use that function. I seen this. I'm going to use the function to get my data set on Boston housing data set. Then when I want to compare all the models, I will need to use root mean squared error. So the root mean squared error is going to come from the scikit-learn metrics. We have different metrics that we can use to compare models. We have the mean absolute error. We have the mean absolute percentage error. So I'm going to use mean squared error. And I'm getting this function from the scikit-learn library or the scikit-learn.metrics module. And the last thing is to split my data into two groups. I'm going to split my data into two groups. When you want to fit a machine learning model, you try to avoid what we call overfitting. Overfitting means your model performs well in the data you use to train it. But if you want to use the model to predict for future data, new data sets, it doesn't perform well. So we say the model was overfitted. The model can perform well on the data set used to train it, but the model cannot be used to estimate or to predict for new data sets. The essence of fitting a model is so that this model can be used in real life application to estimate for new data sets. Like this, our data is to estimate the worth of a residential building. Now, if someone meets me and tells me he stays at Boston and give me all the variables I need, new data set, can I use my model to estimate the worth or the value of his building? If my model cannot perform well on new data sets, then that model was overfitted, and that's bad. How do you overcome overfitting? One of the ways to overcome overfitting is to split your data into train and test sets. There is no fixed rules for this. Some researchers use 80% of the data set you have to train it, then 20% to validate or to test it. So we use the test set as a new data set and see how the model is going to perform on the test set. What I mean is we are going to use only data from the train set to fit and estimate the parameters of the model. And after doing that, we'll then use the model to predict values for the test set. The test set was not used to train it. If the model performs well in a test set, that model is good and can be used in real life application. So you have to avoid the problem of overfitting. And to split our data, there is a function in Python that helps us to split our data. You can do that yourself. Like when I do arrow code, sometimes I write my own code to split my data. But since there's a function to use, why write your own code? Just import the function and make use of the function. So we're going to use the train test split function, and it's coming from the scikit-learn module selection, model selection module. Then what we have next is this is coming from this library. Some people call it NumPy, or don't know what you call it. So we're going to use this. So what does it do? Now, if you want to make sure anytime you run your analysis, you get exactly the same results, we are going to use this for our machine learning models. Like when we start doing artificial neural network, random forest, Gaussian process regression. Whenever you run these models, it gives you, if you run it the first time, the result you get will be slightly different from the result you get when you run it the second time. And this is because of the optimization technique and other factors being considered. Now, if you want to get exactly the same result anytime you do the analysis, you have to set seed so that you'll be able to replicate the results. If you are working on any model, the good thing is for you to be able to replicate it. Because you can't get a result now, and you are finding it difficult to get exactly the same result you use. For example, if you want to publish a paper, and let's say after first submission, they ask you to review your paper. and you are trying to get the same result, but you can't get it because you didn't set seed. So always set seed so that you can replicate your result. Then the next code is just to fetch the data set. The data set we are going to use the data set is from Python, or you can also get it from Kaggle. So Kaggle so if you check here, you see Kaggle is a website. You can get it from Kaggle. So the code is to fetch it. So let me run this. Correct. Then the next is to whenever you want to make comments to explain your code and make your code to be readable, you use the pound sign. Now I want to split my data and tell Python, these are my predictors and this is my response variable. So Python is going to classify this as X from henceforth, then classify this as Y. Now let me explain this. This Boston is coming from this. It's coming from this because I named it. So if I change the name to A, then this will become A, and this will be A. So that's what it means. Then in this name, this file, we have the data values for the predictor variable. When I talk about predictor, I'm talking about the independent variables. We also have the Y variable. Let me check something. So this is my data. If you want to get your your predictor only, you do dot target dot values. So it gives you the Y variable. But if you do dot data dot values, it gives you the X variable. So that's what I did here to get my X only and my Y. So whenever I want X, I will call X. Whenever I want Y, I will call Y. So know that this is X and this is Y. So what I'm doing here is to split my data. Oh, see this as X from henceforth, see this as Y from henceforth. Now let's fit the linear regression model. From our scikit-learn library and the scikit-learn.linear_model module, we are going to import the function linear regression. You can decide to write your own code for linear regression without using the scikit-learn library. If you know the formula for multiple linear regression, you can write the formula and estimate the parameters yourself. But why do that? Why should you do that if you have a function in Python that can help you to do that? So we have a function Python called linear regression. And where can you find this function? You find it in the scikit-learn library, like scikit-learn.linear model module. So we're going to find the linear regression there. So you import it. You import this. Then the first thing is, I can call it, you call the name of the model, you can call it model or I call it anything. I can call it linear, I can call it linear. But anything you want. Then you call your function, the function that I imported. So this linear regression function. So that's the first step, linear. The next step, so in this case, I'm creating a linear regression model. Then the next step is to tell Python, this is my X variable and this is my Y. Okay, I think I skipped this. So let's go back to this. This is where I explained avoiding the problem of overfitting. You split your data into train and test sets. So that's what we use, remember this function are imported from the scikit-learn library, the scikit-learn.model selection module. So I'm going to use this function to split my data. You can do it without using the Python function. But why do it yourself? Why write your own code, stress yourself to write code when there's a function in Python? So I'm going to use the function in Python. So if you are using this, I will explain what this means. So you use the train set. So this is a function. Like in the last video, I said you can create your own function by using def. Now this is a function. The first step in your function is to tell the function what is the x variable, what is y. Then it will ask you your test sets, what is the size? If you tell Python 0.2, it means train set will be 0.8, test set will be 0.2. Some people use 75%, 25%. So if you want to go with that, then your test set will be 0.25. What is random state? Random state is the same. It does the same thing as random dot the np.random.seed. So that whenever you run the code, you'll be able to replicate your result. You get exactly the same result. Your result will not change. If you don't fix your random state, anytime you run this result, it will give you a different set for the train set and a different set for test set. But when you fix your random state, anytime you run the result, you get exactly the same result. So now this is used to split your data into train and test sets. Then you have to tell Python names to save the result. As you are splitting it, this is where you will save it. Use this name to save for X train. The name is not fixed. You are free to use whatsoever name you want to use. Now, when naming a variable, it is best to use name that you can easily remember. So that's why I'm using x_trains. Whenever I see this, I know that this is the train set for my x variable. Then the next is the test set for your x variable. You can use any name. There's no fix. I can call this predictor for train. I can call this predictor for test. So there's no fixed rule towards that. But it's good to use a name that is easy to understand. The next thing is the train for y and test for y. When you run this code, Python is going to split your data into train and test set. It is going to split both x and y to train and test set. Okay. Now that we have done that, we'll use the train set to fit the model. So we're going to fit the model using train sets. Remember, I'm using this name. The first step I did was to create a linear regression model. Then I will do the linear regression model I created. I will do dot fit. So what dot fit means is I want to fit a linear regression model on the train set, so using the train set. The first thing you should enter is your x variable. So any name you use here as your train set for x is what you will use here. Any name you use as your train set for y is what you write here. So if I change this to pred train, P-R-E-D train, that's what I will use here, P-R-E-D train. If I use response train, I will use for y, then I will change that to response train for y. So any name you use is what you will be using from henceforth. That's why I said you have to use a name that is easy to understand. You run your linear regression. So first I created the linear regression. Then the next step is to fit the model. After doing that, you can now use the model to predict both your train set and your test set. The data set I used to fit this model to estimate the parameters of the model is the train set. Remember, I didn't use the test set to fit the model. Always remember that. Okay. So if you want to see, well, okay, so this is where to feed the model. Now let's say I want to see the parameters of the model. I want to see the parameters before I use the model to predict. So what will I do? If I want to see the parameters of the model, I can say, okay, let me save it as coefficients. What did I use as the name of the model? Linear. So linear, I can use that to select the coefficient underscore. Then I will do print COEF. Okay, so now these are the parameters of my multiple linear regression. So this for the first predictor variable, the parameter estimate for the second predictor variable, the parameter estimate for the third predictor variable. So what I mean is this is B1, this is B2, those that know multiple linear regression. This is B3, this is B4, this is B5. That's it. So this function gives you, now look at this, I've been consistent with linear. Why am I using linear? Because when I created my linear regression, I used linear. If I change this to MLL, then it has to be MLL. I have to be consistent with that. Then here will be what? MLL. So that's how it is. Any name when you want to create your linear regression, but you can't change this. Why can't you change it? Because this is a function that I imported. Are you seeing this? This is a function from the scikit-learn.linear underscore model module. You can't change that. But if it is a name you created, you can change that. Now, after doing that, we can use our model to predict. So that's the next step, using our model to predict. So how can you first you predict for the train set and you predict for the test set. So I can call it Y predict for train set. I'm calling my model now MLL. Double L, not. So I'm calling my model MLL. So I have to be consistent with that. MLL dot predict. So MLL is this the name of my model I created. Then I want to predict. This is a function. Predict. What Python will ask you, what is the set you want to use as your predictor variables to predict? If you want to predict the train set, then you have to use xtrain. If you want to predict the test set, you have to use xtest. So I'm predicting, remember this, when you use xtrain, you are predicting ytrain. When you use xtest, you are predicting ytest. So if I want to predict ytrain, I will use xtrain. Python is case sensitive. If you are using uppercase X, you have to be consistent. It is case sensitive. Now, if you run it, if you want to see your results, you can either use print or just write it. So this is it. So these are the predicted values for the train set. I can now compare my predicted values with the true value and see if they are close to each other. And that's what I will use the root mean square error for. So the mean square error, I will use it to compare what the model now is predicting and what the true values are. Is the model accurate in predicting? Most times the model will be accurate in predicting the train set because you use the train set to fit the parameters. But when you want to use the model to predict new data set that we are not used to estimate the parameters, the model is not going to do well. That's what we call overfitting. I've explained that many times. I'm going to compare the predicted value with the true value and see the error rates. Then let's predict for test, MLL. Remember, MLL is the name I created. You can create yours. Dot predict X test. So that's underscore X test. The next step, we are going to calculate the root mean. Either you can use mean square error or take the square root of it, root mean square error. So I'm going to use root mean square error, not mean square error. Root mean square error. So it's taking the square root of mean squared error. So mean squared error is a function, and a function tells you, you start by writing the y variable for train, the true values. Then the next step is you write the predicted values. So you write the true values and you write the predicted value. So this will be this np dot square root. Let me explain what this does. So if I want to take the square root of 25, I just need to do np dot square root. So this np is coming from this library. Don't forget that. I called it np. You can write the full name if you want. But if I delete this, then I'll be using the full name, but I'm using np now. That's why I'm not writing the full name again. So this is just taking the square root. So what this is doing is taking the square root. Why mean square error is calculating the mean squared error. The function tells you you have to write the true value first, then the predicted value. So that's how the function works. So this is the true value. Remember, y train is the true value from here. Then the predicted value is what I predicted here for train sets. So if you use the the f function also explains it. So that is in the f function. It tells you, so you start with true and the predicted. If you put the predicted, you have to follow the order. The order is true, then predicted. You have to follow the order. So you make use of the f function whenever. So this is my true value. True value means the raw data set. Then predicted means what you use the model to predict. So compare both of them and tell me the error rate. The same thing, do the same for test sets. Compare both of them and tell me the error rate. So you use the f function. If you can make use of f. It gives you examples on how to use a particular function. So you run this. If you want to see your results, you can print your results. So the train MSE is this, while the test MSE is this. So meaning both have similar error rates. That means the model was not overfitted. Like we don't have the problem of overfitting. When you have problem of overfitting, the train error will be very small, while the test set error will be very large. And that's the problem of overfitting. The model is performing well in train set, but doesn't perform well in test set. So the error rate is not that large. So the error rate is 4 points. Okay. So the next time we are going to learn how to use a different model on this data set and see if we are going to reduce this error rate. Remember, what we are trying to do is to model the price of residential building at Boston. So if you tell me neighborhood characteristics like crime rates, pollution, proximity to employment center, and different features, can I use it to predict the price of that particular building? You know, the price of buildings change over time. Like if I buy a building today, and let's say 5 years from now, they build a university close to my building, the worth or value of that building is going to change. Can I use my model to estimate the price? That's what we are trying to do. So we are using different models to do that. We started with multiple linear regression and we have the error rates. Next time, we are going to use a different model and see if the error rate is going to reduce or if it will be exactly the same. So that will be all for today. Thank you. So subscribe to my channel, like the video, make comments, tell me what you enjoyed about this video. If you want me to teach any other thing after this particular training I'm organizing, you can also state that on the comments section. Okay, thank you. Bye.